Hello and welcome to our 2026 Senior Capstone Project, ECE Tesla Candy Bowl. Our team members are Matthew Allery, Gavin Curtis, Nolan Ellis, and Mahmoud Salih, with Dr. Jeffrey Ward serving as the project sponsor. The goal of Tesla's Candy Bowl was to create a safe, durable, and interactive electrical engineering demonstration for GVSU outreach, recruiting events, and other public demonstrations. The project had a total budget of $1,000 and combined several electrical and mechanical systems into something educational and fun to use. The system is powered from a standard 120-volt AC outlet and primarily detects interaction through changes in human capacitance. When a person reaches toward the candy bowl, their hand changes the capacitance around the theremin antennas. The analog circuitry detects that change and continuously varies the audio response. The target sensing range was approximately 6 to 18 inches. The completed system also holds about 1 pound of candy, weighs less than 25 pounds, protects users from the internal electronics, and includes adjustable audio and visual responses. The system is contained inside a clear acrylic enclosure supported by an aluminum frame. The transparent panels allow users to see the internal electrical components while preventing contact with the electronics and high-voltage portions of the project. From the top, the theremin antennas are positioned near the front of the bowl to encourage interaction as a person reaches for candy. Behind the bowl are the Jacob's ladder, LED matrix, and speakers. The side views also show the internal power supplies, wiring, cooling fans, and ventilation openings. These features keep the system visible, protected, and serviceable. The major design criteria included independent theremin pitch and volume control, a vacuum tube audio stage, a Jacob's ladder, an LED matrix, external brightness control, and external volume control. All of these subsystems had to operate together inside one enclosure while remaining safe and visually engaging. The completed theremin controls pitch and volume by detecting the user's hand position. As a hand moves near an antenna, the surrounding electric field changes, which alters the behavior of the analog oscillator circuit. One sensing path controls pitch, while the second path controls volume. The vacuum tube gives the audio a fuller and warmer character. The sensitivity circuit provides a larger response from a smaller capacitance change, allowing the system to begin reacting while the user's hand is still farther from the antenna. The volume control circuit uses a separate antenna to detect difference in hand position. The antenna signal is conditioned by the TL082 circuitry, diode network, and filtering components. That signal becomes a control voltage for the JFET gain stage. The circuit was designed so that moving a hand closer to the volume antenna increases the output volume, while the suppression and filtering components reduce harsh transitions and unwanted noise. The pitch section uses a variable oscillator and a reference oscillator. The antenna changes the frequency of the variable oscillator, while the reference oscillator remains comparatively stable. The difference between those two signals produces the audible pitch. Adjustable components allow the oscillators to be tuned after assembly because antenna geometry, wiring, PCB layout, and nearby grounded surfaces all affect the final operating frequency. The 12AU7 vacuum tube is placed in the audio path to add tube coloration rather than provide the main speaker power. Coupling capacitors block unwanted DC between stages, and a jumper if needed allows the tube circuit to be bypassed during testing. The conditioned signal is then sent to the external audio amplifier and speakers. The first PCB prototype revealed two major issues. The volume circuit did not function as intended, and the internal power plane was not properly connected to the required nets. These problems required both a redesign of the volume circuit and a corrected PCB power plane layout. The second PCB revision corrected the missing power plane connections by properly assigning and connecting the required nets. This version allowed the team to continue subsystem testing, but additional performance problems remained in the volume control and audio output sections. The third prototype operated more reliably, but the volume circuit was still not sensitive enough for the desired hand range. The original LM386 audio amplifier was also insufficient for the approximately 900 mV to 1 volt peak-to-peak input signal. The next steps involved continued use in tuning the antenna spacing, gain, and filtering while selecting a more suitable audio amplifier. The final theremin printed circuit board combined the oscillator, signal conditioning, volume control, vacuum tube, and audio output sections. The original LM386 amplifier was replaced with a TPA3110 amplifier, which was better suited to the available input signal, peak-to-peak range, and speaker load. A diode suppression and filtering circuit was also added to improve the sensitivity and stability of the volume control response. This video demonstrates the theremin responding in real time. As the user changes hand position near the antennas, the pitch and volume change continuously without the user touching the instrument. The LED subsystem uses an Adafruit Matrix Portal M4 microcontroller and was programmed in Python. AVL53L0X LiDAR distance sensor determines which animation should play based on the position of the user's hand. The matrix contains 6 animations, including idle, near range, far range, transition, and scrolling text behaviors. A series of flag variables tracks the sense distance range and controls the animation sequence. The matrix portal also controls a power relay that switches the Jacob's ladder on and off during interaction. LED brightness is adjusted separately using an external potentiometer. This video shows the LED matrix changing animations as the LiDAR sensor detects different hand distance ranges. The sensor selects the animation, while the external potentiometer controls the display brightness. The Jacob's ladder begins with 24 volts DC supplied to a zero-voltage switching circuit. The GVSU circuit drives a flyback transformer, which increases the voltage to approximately 10 to 15 kilovolts. This voltage ionizes the air between the copper electrodes and creates a plasma arc. The hot ionized air rises, carrying the arc upward as the electrode gap becomes wider. Once the gap becomes too large to sustain the discharge, the arc extinguishes and then starts again near the bottom. This video shows the plasma arc forming at the lower electrode gap, rising as the heated air moves upward, and extinguishing when the spacing becomes too large. This full system video shows the completed interaction. As a user reaches toward the candy, the theremin responds with changing pitch and volume. The LED matrix selects an animation, and the Jacob's ladder is activated through the LiDAR-controlled relay. The vacuum tube and speakers provide the final audio response, while all of the electrical and mechanical subsystems operate together. Structural testing was performed to verify that the enclosure could survive transportation and accidental impacts. An FEA simulation evaluated a 3-foot fall and examined enclosure stress and deformation. A physical straight drop test then used approximately 1 pound on top to represent the candy and 5 pounds inside to represent the electronics. The acrylic panels and aluminum frame remained intact without permanent structural failure. A separate pushover test was performed with approximately 6 pounds inside the enclosure to simulate the combined internal load. The enclosure was tipped from multiple orientations and remained structurally functional, with only minor cosmetic wear. After the design, prototyping, manufacturing, and testing phases were completed, all mechanical and electrical subsystems were integrated into the final Tesla's candy bowl. The system responds in real time as a user reaches toward the candy, combining analog theremin sensing, LED animations, the Jacob's ladder, vacuum tube audio, and visible electronics. The result is a reusable outreach demonstration that makes electrical engineering concepts visible, audible, and interactive. We would like to thank GVSU, our project advisors, Mayfair Plastics, and everyone who supported the development of this project. Thank you for watching Team 21's 2026 Senior Capstone presentation.